first sample problem that we did in class, we have this equation, and we have some information in here about how many grams of H2S gas we have at the beginning, the volume of the container, 1.25 liters. We know the moles of S2 at equilibrium. So between all this, we can answer every question that we come across. The first one's the easiest. Write the expression for the equilibrium constant. Okay, so everybody should get this. The equilibrium constant is the products raised to any powers. Right? That 2 corresponds to this 2 and divided by any reactants. And again, here we have a 2 as a coefficient, and here it is again as the exponent. So that's your first point. Then the next question is we have to find the equilibrium concentration in moles per liter, which is molarity, capital M, of the following gases in the container at 483 Kelvin, H2 and H2S. So the first thing that we can notice is that according to our equation, H2 and S2 have a 2-to-1 relationship. So however many moles of S2 I made, which is this number, I'm going to have twice as many moles of H2. And they're all in the same container. So this many moles of S2 divided by the volume times the 2-to-1 relationship tells me that I have 5.95 times 10 to the minus 2 molar HCH2. Right? And that could be written as 0.0595 as well. For H2S, it's a little different because I started with some and some went away. But the amount that went away is easy to figure out. First of all, what we started with was the grams given up here, and the molar mass of H2S is close enough to 34.0. So this first term would just give us our moles of H2S. So this whole thing right here is just moles of H2S. Now I subtract from that the fact that for every 2 of these that disappeared, 1 of these showed up. And I know how many showed up, how many were formed. So if I take this is the number of moles of S2 formed, and I multiply it by the same kind of factor, 2-to-1, then that's going to be the amount of H2S that had to disappear. So moles minus moles, and the whole thing divided by the volume. So the concentration of H2S is 2.05 times 10 to the minus 2. In part C, we have to get the equilibrium constant. So finally, we're going to start bringing all this together. Important thing to remember is that we already know the equilibrium concentrations of 2 of these because we've found them before. Part B, we got concentration of hydrogen gas and the concentration of H2S. So the only one that's left is the concentration of S2, and we were told how many moles we had in a 1.25 liter container at equilibrium. So the concentration of S2 gas is simply the moles of S2 gas divided by the volume. The concentration of S2 is 0.0298. So I combine all of these together. I've got my Kc expression. I have my concentration of H2, my concentration of S2, and my concentration of H2S. And make sure I've got my exponents in for the 2 that had a coefficient in front of them. And when I evaluate it, I find out that I've got a Kc of 0.251. Last thing is I need to calculate the partial pressure of S2 gas in the container. So instead of having to find everything, I just need to find the pressure of just the S2. And I already know the moles of the S2. I already know the volume of the container. I already know the temperature. I can look up R. So that means I can just use the ideal gas law. And with a little algebra, change it so that I'm solving for pressure. That's what this is. And then I substitute in my moles, my R, my T, and my V. So plug them in, and I find out that the partial pressure of S2 is 1.18 atmospheres.